So now we talked about Kc, equilibrium constant, and it was the concentration of the products divided by the concentration of the reactants. So most of what you're going to study in A2, that's going to be applications of equilibrium constant. Like, where do you use these values? So the first and different equilibrium constants are going to have different names. Just like enthalpy change, you have enthalpy change of formation, you have enthalpy change of combustion, depending on what whose enthalpy change you're calculating, and so the names of Kc are going to change. So the first one is going to be called the first one that we are going to study is going to be called Kw. This one is the dissociation constant of water, or it's also known as, so this is the dissociation constant of water, or it's also known as the ionic product of water. Kw is exactly the same as Kc, except that it applies to water dissociation. Now, water dissociation is an equilibrium reaction. So, for example, you have a water molecule. We all know that water molecules, they dissociate and they ionize and they produce H+1 and OH minus 1 ions, right? Is that clear? Abdullah, is this clear? Ruba, is this clear?
Yes.
Now you've studied that whenever you have water, water is going to ionize and it's going to produce these two ions, H+1 and your OH minus 1 ions. The question is, why does water ionize? And the reason for that is that if you have a beaker that's full of water, there would be a lot of water molecules. So there's H2O, lots and lots of water molecules, and these water molecules are all bumping into each other. So it's bound to happen that a few of them would collide, and the bonds in a water molecule might break, and H+1 and OH minus 1 ions are going to be produced. Now, this is an overly simplified equation. This is not the true equation of water ionizing. What actually happens is, we'll be using this equation, but the thing with this equation is that it's an overly simplified equation. The actual equation is this one. That what happens is that two water molecules are going to bump into each other. So if you see the diagram over here, these two water molecules, let's say, they are going to collide with each other. And when they bump into each other, we know that water is a polar molecule. So here's a water molecule, here's another water molecule. Water molecules, the oxygen has lone pairs, which is why the oxygen lone pairs have a partial negative charge and the H is partial positive, because it's a very polar bond. Oxygen is a very, very electronegative atom. Here's another water molecule, and that water molecule also has lone pairs. The lone pairs have a partial negative charge and the H has a partial positive charge. Now what happens is, when two water molecules bump into each other, the H over here is going to be attracted to the lone pairs of this water molecule. And this part over here, this would, because it's negative and this is also negative, the two negatives are going to repel. So the OH minus 1 would break off. Okay, so that's going to get repelled and you'll get an OH minus 1 ion. Because the negative oxygen is going to be repelled by this oxygen over here. The H, on the other hand, would be attracted to this oxygen. So what's going to happen in that case is that this water molecule over here, its lone pairs, which are partial negative, are going to attract the H+1 and they would end up forming a dative bond. Is this clear?
Yes, sir.
TK, is this clear to everyone? Lubena, is this clear?
Yes, sir.
Okay. So this is your actual equation that's happening. The two water molecules are bumping into each other, and you have an OH ion that's getting produced and an H3O plus 1 ion that's being produced. This is known as a hydronium ion. It's this one over here. So remember, whatever you call H plus 1, there is no actual H plus 1 in water. What happens is that any H plus 1 that's produced is going to be quickly attracted to the lone pairs of oxygen in the water molecule, and they're going to datively bond with each other. So there's going to be a dative or a coordinate covalent bond that's going to be formed between the molecule. So all your life you've been studying about H plus 1 ions. So just remember that in reality, what you think is H plus 1 ions, those H plus 1 ions are absorbed by water molecules, and it's actually H3O plus 1 that exists in water. There is no H plus 1 ions in water. So just remember, H plus 1 ion is an oversimplification, what we refer to as H plus 1 ions in a solution that's actually H3O plus 1 ions. I mean, you approximately take them as the same thing. So is this clear?
Yes, sir.
Achha, so
Yeah.
now calling it H plus 1 and calling it H3O plus 1, it kind of means the same thing. It's conventionally you just use H plus 1. You always talk about pH. You always talk about H plus 1 ions. But remember, whenever you talk about H plus 1, you're actually referring to H3O plus 1, because there is no H plus 1 ion swimming around in water. Any H plus 1 ion that's in water is going to be quickly absorbed by water molecules to form H3O plus 1 ion. So I'm going to deal with both equations for dissociation. Both are interchangeably used, so don't get confused if they're using either one of them. Now, in your exam, what would happen is, just a second. I said, now in your exam, what's going to happen is, both equations would be used interchangeably. Some questions would be using this equation for dissociation. Some of the questions would be using this equation for dissociation. Both equations are equivalent. Okay, they can be interchangeably used, and they're both equilibrium reactions. Just a second. And they're both equilibrium reactions. And since they are equilibrium reactions, the fact is that water doesn't really ionize. This is something that we were doing in electrochemistry as well. I told you that whenever you have a solution, when we were doing electrolysis, I told you don't take it as H plus 1 or OH minus 1, because the concentration of H plus 1 and OH ions, it's very less. So the fact is that water doesn't really ionize much. The concentration of H plus 1 and OH ions at equilibrium under standard conditions, that's extremely low. So this kind of shows that water doesn't really ionize a lot. It's 1 times 10 power minus 7 mole per dmq. Or if you're using this equation, it's 1 times 10 power minus 7 mole per decimeter cube, and the other one is also 1 times 7 mole per dmq. So the extent of dissociation is very, very less. We're going to use Kc. What is Kc? Kc is the concentration of the products, which in this case is H plus 1 concentration into OH minus 1 concentration. And it's going to be divided by the concentration of water, right? So because it was an equilibrium reaction, what I've done is I've taken Kc, which is products over reactants. Or in this case, it's going to be Kc is equal to H3O plus 1 concentration divided by into OH minus 1 concentration divided by the water concentration. and that's going to be squared. So anyways, you get these two expressions for Kc, depending on which equation you're using. Remember one thing, that whenever water is in excess, which in this case it is in excess, or anything it's in large excess. So it's in large excess, which means if you have a beaker that's full of water, it's mostly going to be water. The amount of H+1 and OH ions are going to be very, very few. So water is in large excess, and whenever it's in large excess, it has constant concentration. Like if it has 1,000 moles and 1 mole is produced, the quantity of water hardly changes. So it almost has constant concentration. Is this clear as well?
Yes, sir.
So and anything that has constant concentration, you don't write it in the expression. Or what you do is you take it as a constant. So you just add up all the constants. So you pick this water molecule, and you're going to take it to the other side. You're going to combine all the constants together because its concentration is a constant. And the same could be done for the other equation as well. Its concentration is a constant. So you combine the constants together and you get this expression. Now both expressions are kind of exactly the same. It's this is going to be called your, because both Kc is a constant and water concentration is also a constant. You just combine them together and you start calling it Kw. And Kw is H+1 concentration multiplied by the OH minus 1 concentration, or in this case, again, it's going to be kind of the same. It's going to be H3O plus 1 concentration multiplied by the OH ion concentration. You don't write water in the expression because water concentration is a constant. Is this clear?
Yes, sir.
Yes, sir.
Achha, so that's your Kw, that's your water constant. And I told you that the value of Kw, I told you this thing that that the ion concentration under standard conditions at room temperature, it's this. So you've got 1 times 10 power minus 7. The other one is also 1 times 10 power minus 7. So I'm going to substitute these values over here. And what would I get? I'll get the value of Kw, which is going to, because it's a constant, it's an equilibrium constant. It's going to be 1 times 10 power minus 7 multiplied by 1 times 10 power minus 7. And that gives me 1 times 10 power minus 14. And the unit is mole squared because it's concentration multiplied by concentration. So it's mole squared and dm minus 6. Okay, is this clear as well?
Yes, sir. Yes, sir.
Okay, so you have your value of Kw. It's 1 times 10 power minus 14. Now the question is, why is Kw important in the first place? I mean, and remember, Kw is a constant. So its value is always going to be 1 times 10 power minus 14. It's an equilibrium constant. Its value, when does the value of equilibrium constant change?
Change in temperature.
Okay, so it only changes with temperature. Remember, pressure and concentration is not going to have any effect because the equilibrium would automatically adjust. The product and reactant ratio would automatically adjust to maintain that ratio. So no effect of changing concentration or pressure. That's not going to have any effect whatsoever, except for temperature. And what effect would temperature? Can you just guess? Like you have your beaker over here. If you increase temperature, what would happen to the dissociation? Like you increase temperature, the kinetic energy would be more. The molecules would be bumping into each other a lot more. So would there be more dissociation or less dissociation?
Or dissociation.
It's going to be more dissociation because the molecules would be interacting with each other more. They would be bumping into each other, and they would ionize a lot more. So also remember that it only changes with temperature, and at higher temperatures, you have more kinetic energy, and you have more frequent and effective collisions at higher temperatures. So at higher temperatures, there's going to be more dissociation. So more ions are produced, more H plus 1, OH ions. So you're going to have a higher value of Kw. More products are being formed. So higher Kw. So always remember that if you increase temperature, the value of Kw is going to increase as well. So that's all about Kw. But the importance of Kw, why are we studying about Kw? Why is it so important? Why is H plus 1 into OH minus 1, this product, this ionic product of water, and the value being 1 times 10 power minus 14, why is that so important? Now the thing is, the reason Kw is so important is that water is important. Water is one of the most important chemicals on planet Earth. 70% of the Earth's crust is water. And it's your main solvent. All your reactions that are happening in the human body, they're basically happening in a solution that's mostly water. Like blood is water, it's mostly water. So your cells have water. So whenever you hear the term solution, most reactions, they happen in solutions. So we are all dependent on water. So water is everywhere. It's so whenever two things react with each other, like if you have an organism and there are two molecules trying to react with each other. So the two molecules, let's say there's X and there is Y. Now the two molecules would react, but they would be surrounded by water molecules. They would most likely be dissolved in water molecules. So there's going to be a lot of water molecules that would be surrounding them. So X is trying to react with Y, and the solvent is water. Now the thing is that there could be many different types of these solutions. If X and Y are trying to react, lots of water molecules present over here. Some of the water molecules might dissociate. So it's not just water molecules that are present, there might be H plus 1 and OH minus 1 ions also present in the solution. Is that clear?
Yeah.
So if water ionizes, the concentration of H plus 1 and OH minus 1 is going to be equal, right? Because they're both going to be produced in equal quantity. There's going to be H plus 1. If a water molecule breaks up, it produces H plus 1 and OH minus 1. So they're going to have equal concentration. Whenever the concentration of H plus 1 and OH minus 1 in a solution is equal, that's known as a neutral solution, which is referred to as pH being equal to 7. So some reactions, like this X and Y, they're trying to react. Some of the reactions, they would prefer that the conditions are neutral, right? So this X is trying to react with Y, lots of water molecules in between. So they might like that the conditions are neutral. But sometimes what happens is there's some reactions which prefer more H plus 1 ions. Like there might be some reactions that would prefer a higher concentration of H plus 1 ions. Like you would want, those reactions would require, they might need H plus 1 ions in the reactions. So they would prefer more H plus 1 ions. Where do you get more H plus 1 ions? Like if a water molecule ionizes, it produces equal quantity of H plus 1 and OH minus 1 ions, right? So how do you increase the concentration of H plus 1 ions in a solution? What do you do? What thing needs to be added into the water to have a higher concentration of H plus 1?
Adding a base.
No, you add an acid.
Sorry.
An acid specifically produces H. So acid is a molecule you're going to add this random molecule, which is an acid molecule, and that molecule would release these H plus O9. So the amount of H plus O9s in the solution would increase. So some reactions, they prefer these conditions. So this is known as an acidic solution, and the pH is going to be less than 7. And the only way you can have a higher concentration of H plus O9s is that if you add an acid, you add a molecule that releases H plus O9s. And then there's the opposite scenario. Some reactions would prefer that the amount of H plus O9s is lesser and the amount of OH ions are more. Some reactions prefer that you have more OH ions in the solution. So the H plus 1 amount would decrease and the OH minus 1 amount would increase. That's called a basic solution. And the only way you can increase the amount of OH ions and decrease the amount of H plus 1 is if you add a base. TK, is this all clear?
Yes, sir.
Yes, sir. Yes, sir.
So there, like in the human body, there are billions of reactions that are taking place all the time. Every reaction has a particular preference. They would prefer, like this X and Y are reacting together, they would prefer a certain environment that should be around them. The environment is mostly composed of water, but there are three different types of water. One in which is neutral, one which is acidic, and one which is basic. And so all reactions are so when like for example in the stomach, the environment is very acidic. Like all the digestive reactions, they would prefer acidic conditions. Even your blood is kind of slightly acidic. Some reactions or some places in the human are basic. For example, saliva is slightly basic sometimes. So this pH is extremely important because all reactions are going to depend on that. Any reaction that's taking place on planet Earth, that depends on this. Like if you change the pH, the reactions are going to get affected. If you change the environment that's around X and Y might not react if the environment is too acidic, or they might prefer basic conditions. So every reaction has a particular preference. Same is the case with plants. They would prefer a certain pH. So reactions are very sensitive to, most reactions are extremely sensitive to the environment that's around them, which is basically pH. I said, so where does KW come in? Now KW comes in that I told you that what is KW? KW is the product of it's the product of the concentrations of H plus 1 and OH minus 1 ions. So, and I told you it's always going to be equal to 1 times 10 power minus 14. So, over here, if the concentrations are equal, the product would still be, you multiply the two, it's still going to come out to be 1 times 10 power minus 14. If H plus 1 goes up, the OH minus 1 automatically, they come down. But the product would still remain 1 times 10 power minus 14. Vice versa, if H plus 1 concentration decreases and the OH ion concentration increases, the product would still be 1 times 10 power minus 14. So every time, no matter whether the conditions are acidic, basic, or neutral, KW is always going to have the same value, which is 1 times 10 power minus 14. It's the concentration of H plus 1 multiplied by the concentration of OH ions. The two might be equal. There would be more H plus 1, less OH ions, or there would be more OH ions, less H plus 1, but the product would always come out to be this value. Is this clear?
Yes, sir.
Yes.
So the KW value is always going to be like the same, right? 1 to 10 to power minus 14.
It's always going to remain 1 times 10 power minus 14. No matter if it's acidic, or it's basic, or it's neutral. It's always going to come out to be 1 times 10 power minus, because if one increases, the other decreases. If this increases, this decreases. But the product would remain always constant. Is that clear? Okay?
Yes, sir.
I said now, the next thing is what do you do with KW? OH, just one second, OH minus 1, not 14. Now the next thing is what to do with KW. I mean, we know it has a value of 1 times 10 power minus 14, but what do we do with that? What we're going to do with that is that we have a constant need to track H plus 1 concentration and OH minus 1 concentration. I mean, there's a need. Like if you're planting crops, you want to check the pH of the soil. Is it the right environment for the plants to grow or not? Is it the right combination of H plus 1 or OH ions or not? If somebody is having a blood test, the first thing you're going to do is you're going to check the pH. If there's a upset stomach, you're going to check the pH. That's the first thing. What's wrong with the stomach? Is the pH right or not? So every time there's a constant need to track the concentration of H plus 1 ions and the concentration of OH ions. So how do you track that? To track them, you would be making graphs. A lot of times people are making graphs, and every time if you want to scientifically track something or analyze something, you would need graphs. So for making graphs, you would have to do something specific. An additional function has to be applied if you want to track the concentration of H plus 1 ions or OH ions. Now the concentrations could be very high, could be very low. For example, if there's a certain soil, and somebody's testing the pH of the soil every 15 days. On day 1, the pH comes out to be 0.1 mole per decimeter cube, right? Which kind of shows that it's very acidic. So he adds lime, etc., and he tries to neutralize the acid in the soil. I mean, this is the concentration of H plus 1 ions. So on the next, after 15 days, he checks the pH, and it now comes out to be 0.0001 mole per dm cube, right? So that's the concentration of H plus 1 ions. Then after a month, he checks the pH, and it now comes out to be 0.01 mole per dm cube, right? So he's trying to track the pH. So he tracked the concentration of H plus 1 ions. Now, can you plot these values on a piece of graph paper or not? Like, what scale would you choose? Like, if you try to plot these values, one of the values is very small and one of the values is extremely big compared to this one. So whenever you try to plot a graph, the first thing is the values should not have that much of a difference. I mean, the range should be limited. Do you get my point? Like it's
Yes, sir.
like it's easier to plot 2, 4, 8, and 16. Like you can choose a scale for that, right? That is easily plottable. These values are easily plottable. But if you have a very big range, for example, there's 2 and 4, and then there's a value that's 1 million, right? Now, plotting these on the same piece of graph paper, that's kind of impossible. Is this clear to everyone?
Yeah.
Yes, sir.
Okay.
Yes, sir.
So how do you so that's the same thing that we are facing over here. One of the values is relatively much bigger. The other one is relatively very small. So you can't really plot them on a piece of graph paper. You would have to change them. So that's where log comes in. That whenever you make graphs of the concentration of H plus 1 ions, you don't plot the concentration of H plus 1 ions, you actually plot the log of that. For example, if I have 3 values, 10, I've got 1000, and I've got a value which is 1 billion. Now these values are unplottable at the moment, but if I take log, what does log do? If you haven't studied log, remember it's just a function on the calculator. But what a log does is it expresses the value in the powers of 10. For example, what is this value? This is 10 to the power 1, right? So the log of this value is going to be 1. What is this value in the powers of 10? This is 10 to the power 3, right? So if you take log, it comes out to be 3. And in the powers of 10, this value is 10 to the power 9. If you take log, you get 9. Now, plotting these values were kind of They were unplottable, but 1, 3, and 9 can be easily plotted on a piece of graph paper. Is this clear?
Yes.
Yes, sir.
So these are the original values. These are your, this is log based, and if you're, I said these are your log values. Log values are more plottable. So most of the time in the scientific world, whenever you see scales, they're mostly log scales because the range of the values are so. I mean, some of the value might be some values might be very big, some values would be very small. So to manage the range of the values, you always convert them into log scale, and this is exactly what we're going to do. What we are trying to do is we're trying to plot the concentration of A's plus 9s because it's very important to do that in different scenarios. So we're going to take this expression. I'm going to take the log on both sides. So this thing would become, and I'm going to take the negative log on both sides. This thing would become negative log of Kw, which is equal to the negative log of the concentration of A's plus 1 ions multiplied by the concentration of OH minus 1 ions. The reason I'm taking the negative of log is because concentrations are usually in decimals. So can anyone use a calculator and tell me what the log of this value is? And this and this. Or you can just, I mean, what is 10 power watt? 10 power watt is this thing.
-1.
ठीक है, बोल इस्लाम. So this is 10 power minus 1, right? So the log is going to be coming out to be -1. This is 10 power minus 5, I think. So if you take log of this, it's going to come out to be -5. And this would be, I think, 1, 2. This is 10 power minus 2, right? So most of the time, concentrations are small values. They could be very small values or relatively small values. But if you take the log of a value that's in decimal, what happens is you're going to get a negative value. Now, it's kind of pointless to actually make a negative graph because, I mean, you would have to take the negative scale. So just for convenience, what they do is they multiply everything by minus. So instead of taking the log, they take the negative of log so that you don't get negative values. Is that point clear?
Okay.
It's a simple point that concentrations are usually in decimals. So whenever you take log, you get negative values, right? So if somebody is plotting the graph of the concentration of A's plus 1 ions and he's taking the log, he gets -1 one day, he gets -5 on the other day, he gets -2 on the other day. So instead of actually dealing with negative values, you just multiply everything by -1 so that you don't get negative values. So which is why instead of taking just the log, you also multiply it by a negative -1 so that you never get a negative value when you plot a graph. Okay, so that's the whole point of taking the negative of log. So coming to this this expression, which is related, I've just taken the log of this thing. Does anyone know what happens if two things are getting multiplied and I'm taking a log? How can I write that? Has anyone studied log, by the way?
No, I have.
No, you have studied, right? I said, just remember that if two things are getting multiplied and you're taking the log of them, you can also write them as log of A plus log of B. A simple example of that is if two things are getting multiplied, there's 10 power 2 and there is 10 to power 3, right? And you're taking the log of this. What's going to happen over here? It's 10 power 5, right? And if you take log, it's going to come out to be equal to 5. Is that clear? 10 power 5, so that means expressing this thing in the powers of 10 would give you 10 power 5. And that's going to be your answer. So the same thing could be written as log of 10 power 2 plus log of 10 power 3. Log of 10 power 2 is going to give you 2. Log of 10 power 3 is going to give you 3. So that is also 5. So you can, I mean, this is a property of log. If two things are getting multiplied, you can simply add them up. Is that clear?
Yeah.
So the same expression, what was KW? KW was 1 times 10 power minus 14, right? So expressing it in the powers of 10, it's minus 14, right? So this would be minus 14 with a negative sign that's going to become, or I can simply do the, it's KW is 1 times 10 power minus 14. And it's minus log of H plus 1 concentration minus the log of OH minus 1 concentration. If two things are getting multiplied, they're going to get added up in log. Because there's a minus sign, so you multiply everything by minus. This comes out to be 14. This thing over here, the one that I'm marking over here, this thing is known as your pH. And this thing minus log of OH minus 1, that's known as your pOH. And this is the expression that you're going to get. That pH and pOH is equal to 14, where P, what does P stand for? P stands for, it always stands for the negative log of something. So when you write when you write pH, that means it's the negative log of H plus 1. If you write pOH, that's the negative log of OH minus 1. So remember these two expressions. We did the first one. We took the negative log of that, and we got this second expression, which is this one. Is this clear? Shafaq, is this clear? Lubena? Aruba, is this clear?
Yes, sir.
So I'm just going to recap this, what we have done so far. I told you that what you just need to remember is, I told you that water ionizes, and I told you that why it's important that there are three different, everything is happening in water on planet Earth. So there are three different environments, acidic, basic, or neutral. And we learned about the ionic product of water, which is that H plus 1 into OH minus 1, that gives you 1 times 10 power minus 14. That's known as your water constant. It's always a constant. Its value increases if temperature increases. Otherwise, it's a constant. And then I told you that for tracking the concentration of H plus 1, that's very important. You can't really track the concentration of plot graphs using H plus 1 concentrations because the values might be too small or might be too big. So instead, you turn everything into log. You express everything in the powers of 10. So you take the same expression, you take the negative log of everything, and the same expression turns into this thing. The negative log of your constant is 14. This is known as your pH. This is known as your pOH. So you get another expression, which is pH plus pOH is equal to 14, where P stands for the negative log. Whenever you see P, that means negative log of something. TK, is this clear? So we're going to continue tomorrow with questions on this. TK? Clear?
Okay.
Say okay then. Take care. Allah Hafiz.